Streamlines and sketches of fields. We now have vector equations for the electric field intensity resulting from several different charge configurations, and we have had little difficulty in interpreting the magnitude and direction of the field from the equations. Unfortunately, this simplicity cannot last much longer, for we have solved most of the simple cases and our new charge distributions must lead to more complicated expressions for the fields and more difficulty in visualizing the fields through the equations. However, it is true that one picture would be worth about 1,000 words if we just knew what picture to draw. Consider the field about the line charge E equals rho L over 2 pi permittivity rho times A rho. This figure shows a cross-sectional view of the line charge and presents what might be our first effort at picturing the field. Short line segments drawn here and there having lengths proportional to the magnitude of E and pointing in the direction of E. The figure fails to show the symmetry with respect to phi, so we try again in this figure. The real trouble now appears. The longest lines must be drawn in the most crowded region, and this also plagues us if we use lines of equal length but of a thickness which is proportional to E. Other schemes which have been suggested include drawing shorter lines to represent stronger fields, and using intensity of color to represent stronger fields. For the present, then, let us be content to show only the direction of E by drawing continuous lines from the charge which are everywhere tangent to E. This figure shows this compromise. A symmetrical distribution of lines indicates azimuthal symmetry, and the arrowheads should be used to show direction. These lines are usually called streamlines, although other terms such as flux lines and direction lines are also used. If we attempted to sketch the field of the point charge, the variation of the field into and away from the page would cause essential insurmountable difficulties. For this reason, sketching is usually limited to two-dimensional fields. In the case of two-dimensional field, let us arbitrarily set Ez equals 0. The streamlines are thus confined to planes for which Z is constant, and the sketch is the same for any such plane. Several streamlines are shown in this figure, and the Ex and Ey components are indicated at a general point. Since it is apparent from the geometry that Ey over Ex equals dy over dx, a knowledge of the functional form of Ex and Ey will enable us to obtain the equation of the streamlines. As an illustration of this method, consider the field of the uniform line charge with rho L equals 2 pi permittivity. This will make the equation earlier E equals 1 over rho A rho. In Cartesian coordinates, E equals x over x squared plus y squared times ax plus y over x squared plus y squared times ay. Thus, we form the differential equation dy over dx equals ey over ex equals y over x, or dy over y equals dx over x. Therefore, ln y equals ln x plus c1, or ln y equals ln x plus ln c, from which the equations of the streamlines are obtained. Y equals cx. If we want to find the equation of one particular streamline, say one passing through P, negative 2, 7, then we merely substitute the coordinates of the point into our equation and evaluate. Here, 7 equals c times negative 2, and c equals negative 3.5. so that y equals negative 3.5x. Each streamline is associated the specific value of c, and the radial lines shown in this figure are obtained when c equals 0, 1, negative 1, and 1 over c equals 0. The equations of streamlines may also be obtained directly in cylindrical or spherical coordinates. That's all. Thanks for watching.